Hi, Year 9. In this question we read that a cube of side length s sits inside a sphere of radius r so that the vertices of the cube sit on the sphere. And we're asked to find the ratio r to s. And whilst the question didn't provide a diagram, with these kinds of 3D questions it's always helpful to try and create a diagram. Given my limited abilities of drawing 3D diagrams, I've just gone and found a pre-prepared one that represents this scenario. So here we've got our sphere in black and our cube in red, and you have to try and imagine that each of the vertices of the cube are sitting on the outside of the sphere. And I think the key to unlocking this question is to imagine what we get if we connect the bottom corner of the cube to the opposite top corner. The line that results if we connect is effectively going from one side of the cube, of the sphere, to the opposite side of the sphere, and also one side of the cube to the opposite side of the cube. And so by definition that line is going to cut through the very center of the sphere and the cube, which means it represents, in terms of its length, the diameter, because it's going from one edge of the sphere to the other all the way through the middle, which means its length must be the diameter. Now from there we need to try and find a good right-angled triangle that's going to connect that diameter, which we can know is 2 times the radius. If we can connect that to a side length of the cube, then we're going to be able to find the ratio. So I think the helpful triangle is the one that results if we connect the bottom corner of the cube to the opposite bottom corner, and then from there, if we go from the bottom corner that's opposite to the top corner that's opposite, we end up with a right angled triangle with one of the sides being the side length of the cube. Now the bottom side of this right angled triangle we don't know, so I'll call it x. But this right angled triangle at the bottom of the cube, this one here, I'll highlight it in yellow to make it really clear which one I'm referring to. This right angled triangle is going to help us because it has a hypotenuse of x, being the unknown side we'd like to find out, and the other two sides are both going to have a side length of s because they are sides of the cube. So if I redraw that right angled triangle over here, we can overlay what we know about it, and we can use Pythagoras to link x with the cube side length s. So here with this right angled triangle, which is the one I've highlighted yellow in the diagram, the hypotenuse of that triangle is x, and then the other two sides both have a length of s. So from there we can use Pythagoras' theorem to say that x squared will be equal to s squared plus s squared, which means x squared is equal to 2s squared. And we don't really need to do too much more with that because the x, or more specifically the x squared, is going to come into play when we deal with the other right angled triangle, which I'll just highlight in blue to help distinguish. So this blue highlighted right angled triangle is really the one we're interested in, because that's now going to link the radius to the side length. So if I redraw that triangle over to the side, just to make really clear what we're referring to. So for this right angled triangle, being the highlighted blue one, so I'll just highlight it blue so that you can line them up. So the dimensions of this right angled triangle will be d, which we know is 2 times the radius. The diameter is 2 times the radius, so that's the hypotenuse. We have one of the sides which have a side length of s, and the other side length is a side length of x. And now if we use Pythagoras, we will get the hypotenuse squared, so 2r squared is equal to s squared plus x squared, which we just worked out is 2s squared. So from there, we can square the left-hand side. 2 squared is 4, and then we'll have r squared, and then s squared plus 2s squared will be 3s squared. And from there, we'd like to get the r and s onto the one side of the equation so that we can represent it as a ratio. So I'll divide both sides by s squared, and we will get 4r squared over s squared equals 3. And then I'll divide both sides by 4, and we'll be left with r squared over s squared equals 3 over 4. Then I'll take the square root of both sides. So the square root of r squared over s squared equals the square root of 3 over 4. And we can, if we're taking the square root of a fraction, that's the same as taking the square root of the numerator and denominator individually. The square root of r squared is simply r, and the square root of s squared is simply s. And then the square root of 3 we will leave as the square root of 3, and the square root of 4 is 2. So here we know that r divided by s is equal to root 3 divided by 2. But what we really need to do for this question is to write that as a ratio, because the question wants us to find the ratio r to s. So what I'll do is just over here under the diagram, we'll convert these fractions to ratios. So we can say r to s is equal to root 3 to 2. And that there is a totally acceptable answer. If you were to leave your answer in this form, that would be totally fine. But what you might see is the ratio written as 1 to something. So if you wanted to do that, if you wanted to convert this ratio r to s to be 1 to something, you could just say that r to s is equal to, and you could divide both of these components of the ratio by root 3. So we'll get root 3 over root 3 to 2 over root 3. And in doing that, what happens is we get r to s is equal to 1 to 2 over root 3. And that's another way that you might see this ratio represented. So that's how you deal with that question. Quite a tricky one, I think, particularly in terms of visualizing it. And then once you've got that visualization, knowing what to do, like having that light bulb moment where you can notice that going from one corner of the cube to the other effectively gives you the diameter. From there, I think you can then use the various right-angled triangles without too much difficulty, just applying Pythagoras' theorem. But as with most 3D trigonometry questions, the really hard part is in working out where those triangles are. So hopefully now that you've seen this working out, that's helped you in understanding how this question works. And if you ever saw a question like this and you had to do it on your own, hopefully you'd be well placed to do that. All right, tick boom.